4.9 is the chi-squared goodness of fit test. You're going to learn how to test hypotheses using the goodness of fit test, which is a tad bit different from your normal chi-squared test, um, in the sense of it tests a few different things than what chi-squared does. It does have some similar features. However, but the conclusions you'll make, they do differ. You are going to need to know which is which for both tests, and you're also going to need to know the steps as well. So, to give you a little bit of background, is that this test, the goodness of fit test, is a hypothesis test, and it considers a population mean. Okay, very similar to a t-test, which you'll learn next week. These are hypothesis tests, and they are considering a population mean. It is about making claims about population proportions. Okay, so for example, and this will be the example that we use for the entire problem so you can see how the goodness of fit test goes, is that suppose Rico rolled a die 60 times and obtained the rolls in the table. Since the relative frequencies, or better, the proportions of the outcomes are quite different than the expected outcomes, Rico claims that his die is biased. Now, the goodness of fit test allows us to test the hypothesis about population proportions, as what was stated before, and this is where you would do it here. So the type of question that would be asked is use a goodness of fit test to determine if Rico's claim is um, Rico's claim is valid or something of that nature. Okay, and so let's go ahead and start with the steps. So step one is you want to write out the hypotheses. Okay, the hypotheses from before with chi-squared, the regular chi-squared test was the null hypothesis and the alternative hypothesis. Okay, you have something similar here as well. We are going to consider the scenario with k categories. We're going to let P sub I be the population proportion of the individuals in the category I, where P1 plus P2 plus all the way up to however many categories we have is equal to 1. Okay, so but that kind of how this breaks down is that your goodness of fit test, it does have a null hypothesis and alternative hypothesis, but this time, like, the general makeup of what the goodness of fit test is what you see here in this line. Okay, or these two lines actually. So it says basically P sub 1 equals P sub 0, 1, P sub 2 equals P sub 0, 2, and so on and so forth, depending on how many categories you have. The alternative of the alternate hypothesis is basically saying at least one of those categories, at least one of those, does not equal the actual proportion. Okay, so where P sub 0I is the population proportion of the particular category, that's under the null hypothesis. Okay, so remember, our ongoing example is talking about Rico rolling a die and observing all his different outcomes. So our null hypothesis, if you roll a die, the probability of the, or the proportion, or the probability of you getting a 1 or a 2 or a 3 or 4 or 5 or 6 when you roll it is 1/6. So the probability of me rolling a 1 should be 1/6. The probability of me rolling a 2 is 1/6. Probability of rolling a 3 is 1/6, and so on and so forth for each of the times that you roll. That is our null hypothesis, basically what is supposed to be true for this particular situation. Okay, so again, since we're rolling a die, the proportion, remember proportion is a fraction, which can also be represented as a decimal, so on and so forth, is 1/6. Okay, so our alternate hypothesis would basically say that at least one of these, 1, 2, 3, 4, 5, or 6, should not equal 1/6. Okay, so it's basically saying the opposite of whatever the null hypothesis is saying. Step 3. Now I know you're like, wait a minute, Ms. Anderson, where's step 2? Step 2 is kind of combined with steps 4 and 5. And so I'm going to go ahead and do step 3, because really and truly to do to find your test statistic, which is what you're supposed to do in step 3, when you use it with your calculator, you'll actually do steps 2, 4, and 5 like all at the same time. So step 3 is important. because sometimes you'll be asked to do different parts of this particular step in a problem. Or if you ever were to do this by hand, this is how you would do it by hand. And then you would go into the other steps that remain. Okay? So, um, we're going to calculate the test statistic. We use this formula that you see here. If you notice, this is the exact same setup that you would do to find your test statistic for the chi-square test. But because the directions say use the goodness of fit test, you'll know that you'll need to use this formula, which is a little bit different. It is the sum of your observed value minus your expected value squared divided by your expected value. Okay? So, for our example, we have the number that's on the particular die. We have what Rico observed. Remember, these numbers right here that are in this column come from the original problem, from that yellow table. This is what he observed when he rolled the die, okay, 60 times. But remember, what's expected, if this is supposed to be a fair die, we should get the same amount for each time we roll the die, okay? So what I want you guys to do for a second is I want you to pause the video and I want you to actually fill out this table. It's very simple. In the first column, you're just subtracting your observed value from your expected. So you're subtracting this column from this column. Then you're going to square, excuse me, all the values that are in your fourth column. And then you are going to divide each one of these values that are in this column by the expected frequency. And then I want you to sum them all up at the end and then tell me what you get for your chi-squared value. So go ahead and pause this video. When you are ready to see the answer, press play. So hopefully this is what you got for your table. Again, it was very simple. You just had to subtract this column from this one. You had to square the values in this column, and then you had to divide all the values in this column by the expected frequency column, and you would have gotten these. So then you were supposed to add them all up, and then that's going to give you your chi-squared your chi-square test statistic for your goodness of fit test. So you should have got 13.8. And that's how you do step 3. Of course, this is by hand, and there is a way to do it in your calculator, which I'll show you in just a second after I've gone through the steps. Okay? So, in order to make a decision on whether or not you're going to reject the null hypothesis, it's going to be based off of this value, or it's going to be based off of your p-value, depending on what the question asks you to find, what information you're given as well. Okay? So we're going to look at it from the p-value perspective. Okay? So in order to make a decision on whether or not to reject the null hypothesis, you need to calculate the p-value and compare it to the significance level. This is not changed from the chi-square test. You still compare the p-value with the significance level. Okay? Now, in a goodness of fit test, if your null hypothesis is not true, then the difference between the observed frequencies and the expected frequencies would be large. This is what you're seeing over here in this graph right over here. Hence, the value of the chi-squared test statistic would also be large as well. Okay? So that basically means that if it's not true, then the difference between your observed values and your expected frequencies would be very, very large, which means that that this value, if you look at this as an x and y axis, this value would be something that's very large, which means the area underneath the curve, kind of like from normal distribution, will be very, very small. Okay? Now the p-value is equal to the probability of observing a value greater than or equal to the test statistic. Okay? And that is what the p-value is. If you were wondering what that was from the chi-square test, that's what it is. Okay? That is that value there. So along with this, now this is, so step 2 is when you basically determine what is your significance level, okay? Whatever your significance level is, because that's what you're going to compare with the p-value. So that was step 2, and so now you do step 3 to figure out, what the chi-square test statistic is. And again, I'll show you how to do it in your calculator in just a second. So steps 4 and 5. You have to determine your degrees of freedom, just like you had before. Now, in a goodness of fit test, the value of the degrees of freedom is the number of values that are free to vary. Okay. Now, there is a formula that's different from the one from the chi-square test to find the degrees of freedom. You do this by taking the number of categories and subtracting it by 1. Okay, now the number of categories is going to be dependent on whatever the situation is. So for our example, our degree of freedom is 5 because we had 6 categories. The categories were the outcomes of the faces that were on the die when we actually rolled them. Okay, and so then based off of that, whenever you calculate the p-value, you reject it if the p-value is less than alpha, which stands for your significance level. So if your p-value is less than your significance level, then you reject it, okay? If it's not, then you fail to reject, okay? Or you do not reject. Try to refrain from accepting your hypothesis. Don't say you accept the null hypothesis, because the thing is that when you fail to reject, that just means that whatever your null hypothesis was not true. That doesn't mean the exact opposite is true. It just means that the null hypothesis is not true. Okay? And then of course you interpret your decision in context of the problem. So then that's when you would say that because the p-value was this and it was less than the significance level, which again will be given to you in the problem, then that means that Rico's die is not biased, or it is biased. Again, depending on the p-value and the significance level. Okay. So how you do this in your calculator is actually pretty simple. I am going to go back to this slide because I need the information from this slide. I need my observed frequencies and I need my expected frequencies. And I go into my calculator. And because this is data, I'm not going to go into my matrix to type in my information. I'm going to go into my list. Okay, so I go to stat and I go to edit and I need to type the values into my list. Okay, so in L1, you're going to put your observed data. Okay, so in L1 is your observed. L2 is your expected. So the same way that it was in the table, this right here is going to be L1, and then your expected value is going to be L2. Okay, so go ahead right now in your calculator, go ahead and type that in, L1 and L2. Now what you do that, you want a second mode, you want to quit out of it, okay? And then you want to go to stat, go over to test, and remember when we were doing this for chi-square, we went to option C. Well, as you can see, below option C is D, your chi-squared goodness of fit test, the GOF test, goodness of fit. So you go there and you click enter. Again, that's stat, go over to test, all the way down to option D. Now, if you did type your observed into L1 and you're expected into L2, it should pop up, it should populate as so. If for whatever reason you mix them up, you got to make sure that you change this here. If you put observed in L1 and expected in L2, it will default into this. You probably going to have to type in your degrees of freedom depending on your calculator and what's been done on it. So all you do is, you just click enter, and then you'll type in 5 to get your degree of freedom. Then you go to calculate, and you have your p-value. You have your chi-squared, and you have your p-value. Now, remember when we calculated the chi-squared, it was 13.8. So that must mean that I must have did something wrong. Okay, so then what I want to do is I want to go back, and I want to check my list to make sure I typed in everything correctly. 20, 10, 5. There's my problem. I put a 6 when I should have put an 8. Okay, so I guess there's one benefit about doing it by hand. I can make sure that my values are supposed to match. Okay, so I make that an 8, 7, and 10. All the other ones are 10. So again, I quit out of that. I go to stat. I go over to test, and I go to option D, which is my goodness of fit test. My observed was in L1, my expected was in L2, and my degree of freedom is 5. So then I calculate, and there we go. Yep, my chi-square test is 13.8, as it should be. My p-value does change, as we can see. And then we have our degrees of freedom. And it's actually quite interesting. You see those values right here? Those are the same values we got here when we actually did it by hand. Okay? So our p-value is, rounding to 3 significant figures, 0.0169. So our p-value It's 0.0169. Now, let's say that we were going to compare this to, um, let's say we were going to compare this with a significance level of 5%. Okay? Well, if we're comparing this to 5%, then that means that this p-value would be less than 0.05. Remember, to convert a degree to, to convert a percentage to a decimal, you want to move it to the left 2 places or divide by 100. And since 0.0169 is less than 0.05, then that means that we would reject our null hypothesis. Okay? So what that basically means is that if we reject our null hypothesis, which was basically saying that each of our roles should show up, 1/6 of the time, then that basically means that there isn't. Sorry, I have to type this in because I'm not at the school, so I don't have my pen. There's not enough evidence to reject the null hypothesis. Save some space. And it's in favor of the alternative hypothesis. Again, we're not saying that the alternative hypothesis is correct. We're just saying that, it's possible that we might be in favor of the other option. Okay? So, Rico's die is biased. Okay? So, Rico's die is biased based off of the fact that we had to reject our null hypothesis, saying that it was all equal. Okay? But that's what it means to make sure you interpret it in context of the problem. But these are all of your steps. Again, with step 5, you're going to reject the null hypothesis if the p-value is less than it's less than the significance level. Okay. If you use your chi-squared test statistic, okay, so if you use your chi-squared test statistic at this step, I'm gonna actually type out the word chi, so then that way, you guys know that I'm talking about the chi-square test statistic because they don't have a really good symbol in this program for it. Okay, so the chi-square test statistic, okay, you compare it with the critical value. So they will give you the critical value if you were going to compare that then, okay? So then if the chi-square test statistic is greater than or equal to, and I'll add that in just a second. If it's greater than or equal to the critical value, then you also reject as well. So add that in there as a note. Depending on what you're given in the problem, you might have to compare the p-value with the significance level or the chi-square test statistic with the critical value, just like with the chi-square test. Okay, but if the chi-square test statistic is greater than the critical value, you reject. If it's less than, then you fail to reject. Okay, so hopefully you guys, that makes sense. Okay. What we're going to do to wrap up this lesson is we are going to look at this example here. It says the table alongside shows the grades received by university students. Let me make sure I'm still recording. Taking a second year computer science course. In the following semester, a new coordinator is appointed for the course, and a new coordinator is concerned by the high number of high distinctions and distinctions awarded, and wanted to determine if the course needed to be adjusted. Okay, it is considered that usually 5% of students receive a high distinction, 10% receive a distinction, 15% receive a credit, 40% receive a pass, and the remaining 30% receive a fail. Conduct the chi-square goodness of fit test to determine whether the course should be adjusted with a 5% significance level. So a lot of information in the description. You want to make sure you read it all, and of course we have the table. Now the table tells us the frequency in which the previous semester science course, how the awards were given out. But we have what is the usual, okay? The usual here is our expected value. So all these numbers are going to be important when it comes to us doing our goodness of fit test, okay? Now we are going to determine if the course should be adjusted with a 5% significance level. So that means that if we're using the significance level, that means we are going to be comparing it to the p-value. All right, we are going to do this using our calculator to make sure that we don't so to make sure you guys have the practice that you need. Okay, so in order to do this, we need to write out our null hypothesis. Okay, so I'm going to come over here and I'm going to type this out. Our null hypothesis for this particular situation. Okay, remember, this is when you're using the null hypothesis. This is when you're using the proportion of the category. Okay, so P1 represents high distinction, P2 distinction, P3 credit, so on and so forth. So that means for my null hypothesis, P1, which represents my high distinction, should be equal to what? Should be equal to 0.5. Because remember, it's based off of the expectation of what it should be. P sub 2 is equal to 0.10. P sub 3 equal to 0.15. I'm doing these dramatic pauses because in my mind, if this was in class, I would pause, you guys would respond. So hopefully you're responding while you're at home. P sub 4, which represents the pass, is 40. And then lastly, P sub 5 is equal to 0.30. Now, if you were thinking, well, why are they not all the same like in the last problem? Well, remember, in the last problem, we were rolling a die. So the probability of actually getting one of the sides was all equal. So that's why all the null hypotheses were all the same. But in this particular case, they're not all the same. So it can be the same, like in the first example, or it could be different, as we can see here. Okay, so then we also have to do all alternate hypothesis, which would be at least one of the p's. Okay, let's just say p1 does not equal 0.05, and again, this program it's user friendly if I'm typing, if I'm like writing on the board, but not if I'm typing, which is what I have to do here. Or if the value of P2 does not equal 0.1, and so on and so forth with all the other values. Okay. So like P5 does not equal 0.30. Okay. All right. And you can use that ellipses after you've done like two and then you end with the last one instead of having to write it all out. Now I would say for the null hypothesis, I would write out each one, especially if they're all different. But if the probabilities are all the same, then use the ellipses. Okay. All right. So that's step one. Okay, step two is step two is when you identify the significance level. So we know the significance level is equal to 5%. That one's easy. And now we have to calculate the p-value, the chi-square test statistic. Well, since we're using the 5%, we're going to be doing the p-value. So remember, this is where we go into our calculator. This is where we need our L1 and our L2. Remember, L1 is our expected. No, L1 is our observed, and L2 is our expected. Now, here, since this is what we observed, this is going to be our L1. So that's easy. But the thing is that we need to determine what our L2 is going to be. Now our L2, which I'm going to do in orange, and I'm going to put it over here, and I'm going to put it pretty small. Okay. Now the thing about our L2 column is that we have to find the expected. Now we talked about finding expected values back in normal distribution. Expected values were found by taking the number and multiplying it by the probability. So here, since we have the probability, or we actually have the percentage of each one of these awards, high distinction, credit, fail, etc. We need to take those probabilities and we need to multiply them by the number, um, by the number. And in this case, the number is going to be 151 because 151 were the number of students or the number of awards that were appointed for a particular course. So N represents the total, and then P represents the individual probability for each of the awards: high distinction, distinction, credit, pass, fail. Okay, so in order to find our high distinction, we need to multiply 151 by the probability of actually having a high distinction, which is 0.05. We would do the same thing with distinction, except we'll multiply 151 by 0.10. For credit, we're going to do 151 times 0.15. For pass, we're going to multiply 151 by 0.4. And then for fail, we're going to multiply 151 by 0.3. So go ahead and do that and get all my values for my L2. I don't have to add them up. I just need the values because, again, that's what's going to go into my L2. Pause this video, figure that out. Hopefully you guys got these values. And so now what we can do is we can actually go in and find out what our p-value is using our calculator. Okay? So some of you guys might have went ahead and already figured out what our p-value is. And there's no way I can put this. Okay. All right. So remember, we go into stat, we go into edit, and we need to type in L1 are observed and L2 are expected. So I go up to L1, press clear and enter. L2, press clear and enter so I can clear out my list so they're all nice and clean. And now I'm going to type in my values. My observed in L1 and my expected into L2. Okay, so again, once we have it all in there, then remember we have to quit out. And then we go to stat, go over to test, option D. Again, dramatic pauses, so hopefully you're talking this out in your head. Observed is in L1, expect in L2. My degrees of freedom, is my degree of freedom 5? No, it's not. My degree of freedom should be 4. Remember, degree of freedom is your number of categories minus 1. And since we have high distinction, distinction, credit, pass, and fail, that's 5 categories. So we subtract that from 1, and that's how we get 4. So then we go down to calculate, and then we'll get our p-value. And hopefully everyone got this. And of course, we're going to round 3 significant figures. You start with your first non-zero number, which is the 5. So it's going to be 5, 2, then the 9, because 5 is going to cost the 9 to round up. So our p-value is 0.00529. Okay. That's step 3. Okay. Now step 4, we want to go ahead and we want to, well, 4 and 5 they kind of merge together because this is when you determine if you accept or reject. Or am I off on my steps? Okay, I am. Okay. Sorry. This is step 4. I knew I was off a little bit. Step 4 is p-value. Step 3 is the chi-square test statistic, but we had that already in our calculator when we figured everything out, 14.7. But I really don't need it because I'm going to be using my p-value to determine if I accept or reject. So in step 5, remember, you compare. I'm comparing my p-value to my significance level. Now, is that less than or is that greater than my significance level? Hopefully you notice it's less than the 5%, okay? And if it's less than that, that means we are going to, all right, L2 stuff, I'm going to move you kind of out the way. Start typing again. So we are going to reject the null hypothesis. Okay, we're going to reject the null hypothesis. And again, there is not enough evidence. There's not enough evidence to support. And again, you orange L2, you are in the way. Okay? So then for step 6, in context of the problem, what does that mean? In context of the problem, what does that mean? Well, then that means since we have rejected the null hypothesis, that basically means the null hypothesis, which was that we are going to conclude that the course should be adjusted. Okay? Again, when we reject the null hypothesis, okay, that means there's not enough evidence to support that there is the balance of the usual 5%, 10%, 15%. Okay, there's not enough evidence to support that. So then that means that at least there's a possibility that at least one of them does not equal those given probabilities. Okay, so we could say that the alternative hypothesis is something that we can go with. Okay, but this basically gives the new coordinator the evidence that he needs to make sure that yes, these courses are going to need to be adjusted because they're not giving out they're giving out too many high grades, okay, when it should be more of a balance. Okay, I hope this makes sense. Give the homework a try. I will be online during the office hours to help, um, and just bring your questions. I'm also available through Schoology. If it's in the evening hours, it's going to kind of be, whenever I check my phone. But during the morning hours, early afternoon, I will be by my phone a little bit, and I'll be able to respond a little bit quicker. Okay? Right.